so that the folks who are not here, if they listen to the YouTube, I thought I straightened this thing out. Yuck. I have been fighting with these tangles in the wires, and it's been yanking stuff all over the place. There, I think I've got it straightened now. I thought I got it straightened earlier, because they keep, every time I do something, it pulls everything else around. Okay. Okay. Now, for those just joining, I was fighting with wires. Sorry about that. But I had a question before I turned on the recorder about where do you submit research paper, and the answer was you can either submit it as an attachment to an email and send me the email. You can put it as an attachment to a Blackboard message and send that to me. Oh, and here's Andy. Let me get him in here, and I'll start that over again so he can hear it as well. Let me get him marked in the book also. So we have the top half and the very bottom. We're still waiting on Ashton. Hopefully Ashton will be coming in soon. Good morning. Just had a question on where to turn in the research paper, and I was in the process of answering that when I saw you come in, so I thought I'd stop and say it after you got here. You can either attach it to an email and send me the email, or you can attach it to a Blackboard message and put it under Blackboard messages, or you can, and this week, at the beginning of the week, I was doing the week activities, you know, in Blackboard, how they have the weekly activities, and you have 16 weeks listed, and we're in week 15 right now. And in week 15, there's always a place there that I put something for homework, okay, that if you wanted to submit homework there, you certainly could. You don't have to, but you could. And then there's another one there that usually says assessment, I believe it is. Yeah, the homework originally said assignment. I changed it to homework. And then the other one was assessment. And occasionally I put test there when they allow me to. And since there's no test to put there for the Blackboard, I put on assessment, I put the research paper, and you can submit it that way if you want to. To me, that would be more difficult and more complicated because I don't really like Blackboard operations too much. But if you're doing that in all your other classes and you find it an easy, simple way to go, by all means, I'll be checking it, and you can send it to me that way. So any one of three ways. I've actually had students mail me stuff, but it's getting sort of late in the term to be mailing me stuff, so I wouldn't say mail it to me snail mail. Okay, it would be next week sometime probably before I got it, and I'd rather have it sooner than that. All right, good question. Any other questions? Okay, I can't answer that for certain without looking here. I know I haven't graded it yet, and let me see if I received it. It's when? In October. Okay, there is a chance I printed it then and just haven't graded it, but there's another chance that I didn't find it, because back in October I was having some issues with a variety of things, health being one, but also the internet here was giving me problems, and then we have a wireless printer in another room, and that's where I do my printing, and my computer and the wireless printer had quit communicating well, so I got way behind in printing, and the odds are it's still out there. If you ask me right at the end of class, I'll try to check and see if it's there, and then I'll either print it on the spot, or this afternoon I've got 2 hours of office hours, and I'll try to print it then. Let me see if my 2 hours of office hours are free, because let me see if I have any appointments. No, I don't have any appointments, so they should be free, and I'll try to print it then if I haven't gotten it printed yet. But you can, if you want to, you can wait at the end of class and I'll check it, my emails, to see if I got it. The odds are I did, but there was a time frame there when the systems were not working well and I wasn't working well with my much of the month of October and the early part of November. I was critically anemic. I didn't know that at the time. I found out later. That's why I was feeling so incredibly bad. Okay. I was being short of breath. My chest would get tight on me. I just didn't know what was happening. I knew I was anemic, and I thought that must be symptoms of the anemia, but it just persisted, and I had no energy. And then when I went in for blood work before the next treatment was scheduled, which I knew I didn't need, they found out not only was I anemic, I was critically anemic, and they panicked. They were saying, you have to get in and get a transfusion. Well, by that time, I was feeling better. Not good, but better. I just started feeling better that last week or so. And so I don't know what it was like before that, but it was pretty bad. So if that's when you sent it, that could be another part of the reason. I couldn't stay up late at night printing stuff, and I just got further and further behind in the printing. So I may not have even seen the email, and I've been trying since then to get caught up with those, but there are so many things coming in so fast. I had one student, it's way more than you asked for here, one student, I think the week before Thanksgiving, had not attended a single class. She had turned in one bit of information, her syllabus acknowledgement or something like that. So I couldn't mark her as a no-show because she did turn in one piece of information. Never attended a class. It was a mini-term class. We have had now 12 labs, 5 tests, about to have the 13th lab and the 6th test, and then got the final exam, and she still has not turned. And she suddenly that week decided, oh, blah, 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 and I'm going to try to catch up on my work. So that's the kind of stuff I've got going on now, is people piling in stuff that was way overdue. And I'm not talking about any of y'all, but I'm talking about in the other classes, especially the big classes. And I'm just completely swamped. So I will check after class, and if I can find your paper, I'll print it probably this afternoon at 4 or sometime after 4 or so. But we'll look for it and make sure it's there. We may even print it on the spot. So if you want to hang around right after class, we'll do that. Any other questions, issues, problems, concerns? Okay. As I don't know if you're asking it for this reason, but you know this is the last day of class for this term. Next week are final exams. So please, if you do have research papers you haven't turned in or earlier tests you haven't completed, please get those in as soon as possible, and I will try to get those graded as rapidly as I can. But I'm way behind on grading. Since I'm way behind on printing, I'm way behind on grading too. But this is actually, looking at it this way, my last Cal 2 class possibly ever. Okay, I'm retiring in February, on February 1st, and since this is our last class, I will not be teaching, as far as I know, any other classes after this. Okay, so this is it, folks. Okay, not for you, but for me. And while we're on that subject, let me go on and say they finally got open the student course evaluations. Have any of you seen those yet? Okay, check your emails. I believe that's how they communicated, through emails, and there probably are instructions there of how you complete those. Now they're doing this, you've done them before, it's still the Smarty valves, but the difference is now it's going through Banner. And I don't know on the student side if that makes any difference at all, but I do know that's one reason they were very, very late getting them loaded, because Banner is a pain in the neck or some other body part, and they were having a lot of difficulty getting those two things to interact together. The first mini-term classes, if any of you took a first mini-term class, those evaluations will be out there for you as well. Please go back and do those as well, because they could not get these. From what I understand, Banner was not allowing them to do this back then. I just heard a noise. I wasn't doing anything. I don't know what in the world is making that noise, but I don't see anyone else trying to get in the class, so Ashton would be the only one. So please do your student course evaluations. If you're having any problems with it, you can either contact me. The better person would be Miss Jamie Glass, Jamie Glass. It's jglass@lawsonstate.edu. She is excellent, and she will be very happy to help you get that figured out. Okay. Any other questions, issues, problems, concerns? All right. Now, while we were waiting for Andy to get here, I was getting the PowerPoint set up. So let's see if it's set up yet. It should be. It's not opening though. There it goes. Okay. And this taskbar that you can't see, but they put it right up in the field, and I'll move it right down at the bottom. Okay, and we'll go from current slide, and all right, this is example. Okay, we're on example. Okay, I'll pick up that in a minute. Hold on a minute. Let me get the whiteboard set up too, because I didn't have a chance to do that before class. Not too much to do here, just moving that taskbar or toolbar out of the way, moving the whiteboard as far to the left and up as I can, so I'll have the maximum white space to work with, and I'll scoot y'all over to the right just a tad. Okay, now where we left off, what we're doing now, we're in Chapter 8, Integration Techniques. We're not doing improper integrals. Okay, Chapter 8, Integration Techniques. 8.7 is integration by tables and other integration techniques. We are on page 568, right at the bottom of the page, and we were doing example 5, but we ran out of time before we got it completed. Okay, so I'm going to have to kind of pick up in the middle of things here. I hope you have your either notes or whatever from last time. Here was the problem. If I could find my pen. Okay, the pen is being very elusive. I don't see the pen anywhere. This is not good. Okay, I don't know why the pen's not working. Ah, okay, I see the pen. Okay, you see it down there? Okay, I can move it around with this, but I can't move it around with the Wacom. So I do believe a connection there. All right, a button had gotten mashed. Okay, and that had turned off Wacom. Okay, yeah, now I've got the pen back. Sorry about that. Okay, here is the problem. Find, now where did I get, oh, I guess I ended in lavender yesterday. Let me go back to black. Okay, find the integral of, okay, the square root of 3 minus 5x over 2x dx. Okay. Now, with last time, we used formula 19. I'm not going to write it down again. With a equal 3, b equal negative 5, and u equal x. Okay? Now, so what we did, that meant we pulled the 1/2 outside. Okay? And so I will write that one. Okay? So that gave us a 1/2, pulling this 2 on the outside, and that gave us the integral of the square root of 3 minus 5x. Yuck, the pen is not doing well. Over x dx. Okay. Now we used formula 9 with a equal 3, b equal negative 5, and u equal x, okay, to produce a form that's like this. So from formula 19, we got this. The square root, yuck, of 3 minus 5x okay, formula 19 gave us this, plus 3/2. The 1/2 came from here. The 3 probably came from there. I can't remember for sure. But then another integral, and this integral was dx over x, that same x that was down here, and this time we moved this downstairs to 3 minus 5x. Now that's what formula 19 had done for us. That was an equal sign that the bottom didn't come through. Now we go to our tables again, okay, because we figure 19 got us so far, formula 19, but we still have an integral there we can't do, and it's not one that 19 will work on. So we move back to 17, which is where I had looked to begin with, and here's what formula 17 says. Okay, formula 17 says the integral of 1 over u times the square root of a plus bu down in the denominator du. Okay, that looks a lot like this, right? Okay, now in looking at that, I would say let u equal x, because everywhere you see an x up here, you see an equivalent u down there. Okay, we'll also have your a from here is your 3 from there, equal 3. Your b from here is a minus 5, so b is equal to minus 5, and that's a really ugly minus 5. Now, I think we used this one before, and last time I believe the a was negative. This time the a is positive, positive 3. So this time we use the upper integral or solution for 17. So I'm going to bring this equal sign down here and bring my square root of 3 minus 5x that we had left over from 19, okay, plus, and here we have the 3/2, that's out front, don't forget that. And now we're going to do the answer for 17. Now I didn't write that down, but I will write it down as we go here. Okay, so I'm going to open a big bracket here and then put what that is. It's 1 over the square root of a. Now if y'all are back there in the integration tables on page A3, which isn't very useful, it's the first page of the integration tables, appendix B, on page A3. It's near the back of the book, but it's in front of the index, in front of all the odd number exercise solutions. It's in front of all that. You finally get to the appendices, and that's where you are on page A3. Okay, so if you get back there and see A numbers, go to A3 and you got it. Page numbers. Okay, 1 over the square root of a. So that's 1 over root 3. Okay, times the natural log, and now you have a big argument here, okay, of the natural log. In the numerator, you have your square root of a plus bu. Well, that's this square root here, so that's the square root of 3, that's supposed to be a 3, minus 5x, okay, minus square root of a, okay, over the square root of 3 minus 5x, plus the square root of 3. Close the absolute value bar, and then you have your plus c. And we could, I think I'm actually going to leave that plus c outside the bracket, not inside. There's really no reason to have it on the inside. We'll just leave it on the outside, and that makes life a lot easier. Okay, there's your answer. Now I'm kind of glad we didn't find some technique that was going to give us that answer, because that looks like that was going to be a really difficult technique. But let's see if we can clean this up just a little bit. That will equal the square root of 3 minus 5x. The minus sign is not showing up. Okay, the x is not showing up. Plus, now, this square root of 3 will go into that 3, the square root of 3 times. So it's square root of 3 over 2 times the natural log of the absolute value, and these you can't do much with, so just write them down. Square root of 3 minus 5x minus root 3 over the square root of 3 minus 5x. 3's aren't writing well either. Minus 5x plus the square root of 3 plus c. All right, that I think is the answer. Let's see what the book got. Square root of 3 minus 5x, check. Plus square root of 3 over 2, check. Times the natural log of square root of 3 minus 5x minus root 3 over square root of 3 minus 5x plus root 3. Close absolute value bar for the log, and then add a c. Got it. All right, so there is example 5. Kind of a really big pain in the neck, but it is doable. Now they mention on the side note here that arc hyperbolic tangent also might be applicable there. I never ever mess with arc hyperbolic tangents if I can help it. So I would just as soon leave it in a log form like this. To me, I don't see an advantage. Yeah, it looks a little simpler on one hand, but then there's all these other things you have to do to get there, and I'd say leave it alone. This is, to me, a handier form. Any questions on example 5? Okay. If not, we'll go back to our PowerPoints. There it is. And we'll go resume the slideshow there. and we finished, okay, example 4 and example 5. So now we're ready for the top of page 569, rational functions of sine and cosine. Okay, and they jump right into integration by tables. Okay, still integration by tables, but now they're doing rational functions of this. So why is my pen not showing up again? This is so aggravating. Oh, that's wrong. I'm going to go to black here. Now I've got it. Okay. Now, my first inclination here would be to get everything in terms of sines and cosines, not sine 2x. So this would be 2 times the integral of sine x cosine x. Now, where did that come from? The double angle formula. Sine of 2x is 2 times sine x cosine x. So I brought the 2 on the outside, and then down here we have 2 plus cosine x. Now that would be, to me, a logical first step before we even go to the table. And I believe the book did that too. That's what was showing up before. Now, actually, okay, if I were doing this, and by the way, the dx is out here. If I were doing this without the tables, I think I'd multiply by the conjugate of this and see what happens there and see what you can pull out of it. Okay? We're not going to do that. We're going to use a table. So let's go to the tables now. Okay. Way back here. And we were on the very first page of the table, A3, there is not a single trig function mentioned on A3. Flip over to A4. Not a single trig function mentioned on A4. Go to A5. Whoa! Here we have forms involving sine u and cosine u. But when you look at those, I don't see any that have sines and cosines in both the numerator and the denominator. There are 56, 57, and 58 which have sines and cosines in the denominator but none in the numerator. So those don't seem to be all that helpful. Then there's forms involving tangent, cotangent, secant, and cosecant. These don't involve those. Then on the next page, the last page, A6, you have some arc sines, you have some e's, you have some logs, hyperbolic, spaghettios. Okay, there's nothing here that has just sines and cosines except that group on page A5. So how are we going to manage that? Okay. Okay. Your denominator at least looks like the most like number 57. Okay. But it's not exactly like it. So I do think we probably still have some work to do. So perhaps my suggestion, which I was just going off the offhanded there, is what we're going to do. Well, let's let them do the talking for us. Okay, we've already done this part. Okay, and now we got something looking just like this. This form right here, though, is not in the tables. We just noted that. So what do we do next? A check of the forms involving sine and cosine in Appendix B show those listed do not apply. Okay? Now, suppose you consider forms involving a plus bu. That's kind of what we've got down here, but it's definitely not what we've got up here. But we do have, if you've got a let u be cosine, you have a form that looks sort of like this. The only problem is wait a minute, of course. The derivative of cosine is minus sine. Is minus sine. So that's where the sine comes from. Okay? Why didn't I think of that? Okay? So that's where get the sine u with the sine x with the dx here. That's derivative of cosine. Then you have something that looks like this. So let's back up a little bit here. I think I'd just back all the way up here. And let's do this if I can find where I put my pen. There it is. Okay? All right. So what we're going to do is what was they were using u? I believe they were. Yeah. Let u, if I can get my pen back, let u equal cosine x. Then du is equal to minus sine x, that's not 6, sine x dx. So there it is. We don't want a minus, so let's make that a plus and this a minus. And so this then would become minus 2 times the integral of u, that's your cosine x, over 2 plus u, that's this, and then your dx is sine x dx is minus du. Well, I already put the minus sign out here, so that gives you the du. Okay, all right. What we did, we used a u substitution to change the sines and cosines into u's. Okay, now go back to the table, not to the sines and cosine ones, but again the forms involving a plus bu. And here we want u over something plus u. And I believe that's, that's number 3, isn't it? Okay. Number 3, formula 3 in the back says the integral of u over a plus bu du is equal to 1 over b squared times bu minus a times the natural log of a plus bu, absolute value of a plus bu, plus c. Okay, now in our case over here, we have the minus 2 in front, but we want our let u equal u. Okay, that's going to be fine. Let a equal 2 and b equal 1. There's the 2. The coefficient of u is 1. Going to be a pretty simple substitution here. Minus 2, don't forget that. So let's write down what we have here as our answer here. Minus 2 times 1 over b squared. Well, b is 1, so that's just 1. And then b is 1 times u, so that's just going to be u, minus a is 2, so that's 2 times the natural log of absolute value, and then this a plus bu is exactly your 2 plus u. 2 plus u plus c. All right. You think we're through? Not quite. You got to go back and do your plug in what your u substitution is. Your problem was in x's. You need to give the answer in x's. So let's do that. U was cosine x. So this will be a minus 2 times the cosine x minus 2 times log of absolute value, and then your 2 plus u here is going to be 2 plus cosine x there. So 2 plus cosine x. Okay? Plus c. Now, actually, cosine is never, ever, ever less than -1. So 2 plus the least value that is a -1 is always positive. So we can lose the absolute value bars and make this minus 2. I'm going to drop from brackets to parentheses. Cosine x minus 2 times the log of 2 plus cosine x, and then close that outer parentheses, plus c. All right, let's see how the book did. Okay. They distribute the minus 2 in, so let's do that. This will be equal to minus 2 cosine x plus 4 times the log of 2 plus cosine x plus c. Okay. Let's see what they got. Minus 2 cosine x plus 4 log. They left the absolute values on there, but they're not necessary in this problem. You can do it with parentheses, because cosine x is never less than -1. And 2 plus a -1 is a positive number, and any other value for cosine x is going to be greater than that. So you don't need the absolute value. It doesn't hurt to put them on there, but it's not required. Now, example 6 involves rational expressions of sines and cosines. Okay? When you're unable to find an integral of that form in the integration tables, try using the special substitution to convert the trig expression to a standard rational expression. Oh, wait, I'm sorry. We should have finished this. Let me erase all my ink, and let's see how they do. We had already seen they did what I did there, broke that sine 2x into 2 times sine x cosine x, and then if I had been paying attention, you would see with u is equal to cosine x, du would involve a sine x dx. So that's what we use, and they use formula 3 just like we did. That's what they got. They still haven't done the u substitution, which they should have. So they let a equal 2, b equal 1, and u equal cosine x. Now that's sort of a stretch. I mean, it seems like to me, and we did that, okay? But they did it all in one fell swoop. And if you don't see it in one fell swoop, break it into smaller pieces, okay? How do you eat a 5,000-pound elephant? One bite at a time. So don't try to swallow the whole thing, okay? Break it down and so you understand every step. So if you let u equal cosine x, just like we did, du is equal to minus sine x dx. So then we have 2 times this will be a minus 2 times cosine x this times du. Okay, the minus out here, and this is here. Yeah. And here they go to gory detail in the other direction, and it seems like pretty obvious to me. You could just make this substitution here, make this bring the minus on the outside like we did, and then this would be a sine x dx is your du with the minus sign up front. This would be u over 2 plus u. But no, they wanted to emphasize how to do that. And if that helps you see it better, do it by all means. Okay? And then they're using a formula 3, but not showing how they did this. They go right to this, which is correct, and then so they went to gory detail here, skip steps like crazy here. Okay, so minus 2 cosine x plus 4, come on, where are you? There we go. Oh, it skipped it. You know, I'm sorry. Okay, when I loaded this PowerPoint, it said there were some problems with it. This must be where the problem is. They're skipping the last step here. See, I press the button, nothing happens. That must have been deleted either when they did the cleaning it up, or that was what was left out in the beginning. So you don't see the final answer, but we gave the final answer. You just distribute the minus 2 inside the parentheses. Minus 2 cosine x plus 4 log absolute value of 2 plus cosine x plus c. In reality, you could change the absolute values to parentheses and be perfectly fine. Okay. Now, here is what I was leading up to before I remembered they did the problem 2. Here is the substitution for rational functions of sine and cosine. For integrals involving rational functions of sine and cosine, the substitution of, oh my goodness, u is equal to sine x over 1 plus cosine x. Okay, this is simply a half angle identity. I don't usually memorize these half angle identities. Look them up and you see this is exactly what it is. Okay, now if you do that, this is such a weird way to say it, cosine x then would be 1 minus u squared over 1 plus u squared. Okay, a bit bizarre how they're doing this, but it would be true. Now what you do here is solve this for cosine. Okay, this thing right here. And it's not an easy process here. Multiply right here. Yeah, not an easy process at all. But they say this substitution will do this for you. And I really don't see where they ever use tangent of x over 2 at all. But maybe they're going to come back and use it in the future. This is really a bizarre thing. Trying to think if the half angle formula for cosine would give you that. It seems like it would be something pretty close to that. And then sine x would be I don't know. I don't know if it's worth our time to try to rationalize this or not. Let's see what happens if we do what I just said. Multiply numerator and multiply both sides by 1 plus cosine x. Okay, so that gives you a 1 plus cosine x times u is equal to sine x, and you would be dividing by u. This looks really bizarre. Okay, subtract a 1 from both sides. Okay, so that goes away. So we have cosine of x is equal to sine x minus u over u. Okay, now what I would suggest doing at this point is multiplying by the conjugate, which would be a sine x plus u. But then you would have a sine x plus u down here too, which doesn't look very hopeful. Okay, now this would give you sine squared x minus u squared. Okay, I don't know, this doesn't look like it's worth our while to do. I think I see a better way to do it now that I'm looking at it. Rather than mixing up the x's and the u's, goodness gracious. Okay, I'm trying to find my eraser key, and that it keeps shutting down the whole program. Okay, I'm not going to mess with erasing it. Here's what I would do. Square both sides. Goodness gracious. And you get u squared is equal to sine squared ux over 1 plus 2 cosine x plus cosine squared x. Okay, and I would monkey around with that for a while, but it's just not worth our time to do. There's the formulas. They say that's the substitution to use them. And they have a little proof down here. Oh, here's the proof right here. Yep, the first thing they did was square both sides. Okay, and then they wrote the sine squared as 1 minus cosine squared. Okay, now if I could get my pen to show up again, there it is. Now let's see if I can get, no! I don't know why this has gotten so sensitive today. There we have it. Okay, let's erase everything. Okay, first step would be u squared is equal to sine squared x over 1 plus cosine x squared. Okay, and sine squared x is 1 minus cosine squared x, your Pythagorean identity, over 1 plus cosine x squared. Okay, now this, I don't know if this is going to be what they want to do. 1 minus, this is 1 plus cosine x times 1 minus cosine x, okay, over 1 plus cosine x squared, which is 1 plus cosine x times 1 plus cosine x. These go out. Good deal. Okay. Now we're cooking with gas. Okay. So here's what we've got. U squared is equal to that. And what I meant to do here, let me see if I can erase now. Okay. What I'm going to do here is multiply both sides of the equation by 1 plus cosine x. So you get 1 plus cosine x times u squared, that's from here, is equal to 1 minus cosine x. Okay, so I'm going to distribute here u squared plus u squared cosine x is equal to 1 minus cosine x. And what we're trying to do is isolate a cosine x. So let's get all our cosine x's on this side. So add cosine x here and here, and subtract the u squared here and here. Okay? These disappear, those disappear. So what do we have now? U squared, okay, I'm running out of room and I'm trying to think of a shorter way to do this. Okay, and okay, you've got two terms with cosine in it. Factor out a cosine. Oh, here is Andy. Oh, I thought Andy was here. Okay, Andy, I hope I didn't leave you hanging there too long, did I? Okay. For some reason I've got on the wrong page here. Yeah, Andy's already here. We still haven't seen Ashton. Y'all haven't heard from him, have you? Okay.
I disconnected because my computer just said it malfunctioned.
Yeah. Yeah. There's been a lot of that going around, so I understand. So here's what we've got. We've got two terms. If I could get the pen to come back. There it is. Two terms with, and it's not drawing now. This is getting so strange. There we go. Okay. Two terms with cosine in them. Let's factor out a cosine. Cosine x, and the term that's left is, I'm going to reverse the order, 1 plus u squared. And that's equal to, and over here we've got all that's left is 1 minus u squared. Goodness gracious, why did it do that? My pen just has decided to quit writing. Okay. It started off strange. Okay, now it's better. 1 minus u squared. And then what we do is divide both sides by 1 plus u squared. And these go away, and that leaves you cosine x is 1 minus u squared over 1 plus u squared. All right, if that wasn't fun enough, okay, then we could put what sine x was. Well, sine x is u times 1 plus cosine x. But we know that cosine x is this thing. You could plug that back in here and you'll wind up with this term. It's not worth taking your time to do. So there's your u substitution. What a weird one, okay? And that happens to be a tangent of a half angle of x, and that leads to this. Those two together lead to this, and your dx, oh man, how in the world did they get a dx out of this? Because they never solve for x. But let's just take the word for it, is that. Okay? You could do, probably using this half angle formula, that's probably where they use it, and take the derivative of that to get your du, and boy, here's the formulas. If you need them, look them up. Okay? And they don't do a thing with them, so why did I waste so much time? Okay? Sorry about that. Homework exercises here. Always look at the concept check. That's a good thing to look at. Homework exercises here would be number 3. It's both a Calc Chat and Calc View. Number 5's at Calc Chat. 7 or 9 are at Calc Chat. 11's at Calc Chat. 13's at Calc Chat. 15 and 17 are both at Calc Chat, with 15 at Calc View. 19 through 39 are all at Calc Chat. 41 through 47 are at Calc Chat, with 41 at Calc View. 41 through 53 are at Calc Chat. 55 through 61 are at Calc Chat. 63 is at Calc Chat. Any of the odds 65 through 71 should be at Calc Chat. Okay. We're not going to do improper integrals. If you need that anytime, if you keep your book, look it up. Okay? It's a pretty good thing, but if it's an improper integral, you can't do it. But you can do it if you're don't include the improper part. If you just include some margin that is included, and even sometimes then it doesn't work. But that's why let's leave it alone for now and move to chapter 9. Okay? Now how much time do we have? About 40 minutes. So let's go to example 9. Chapter 9. All right. And we'll go from current slide. I probably should go on and close this one out. So I won't have both of them open. That may lead to some confusion. So I'll close this one out. And now let's go back and do the new share to 9.1. Okay. And now we'll do from current slide. Well, okay, there we go. Chapter 9 is infinite series. We're not going to be able to do much with it, but let's at least take a look at it. Okay? 9.1 are sequences, not series. Okay? And generally understood to be infinite sequences. Okay? So what our objectives here are to write the terms of a sequence, to determine whether a sequence converges or diverges, and then write a formula for the nth term of a sequence. And then we'll use properties of monotonic sequences and bounded sequences to make some conclusions. Okay? So let's first look at what in the world a sequence is. A sequence is defined as a function whose domain is the set of positive integers. Not the set of all real numbers, not the set of all integers. Positive integers, which you could call natural numbers or counting numbers. That's what your positive integers are. No fractions, no decimals, no rational numbers, no irrational numbers. The domain is only the set of counting numbers, natural numbers, also called positive integers. Although a sequence is a function, it is common to represent the sequences by a subscript notation rather than standard function notation. Okay? Now, part of the reason for that, function notation, when you look at it, you think all real numbers. You always think that, so we usually use the subscript notation, which makes you think integers, because those subscripts can only be integers. Okay? So here's an example of a sequence. You're counting numbers, 1, 2, 3, 4, 5, 6, all the way up to n, and keeps on climbing. Okay? Well, if a sub 1 was the first one of those, a sub 2 the second one, a sub 3 the third one, a sub 4 the fourth one, a sub 5 all the way, a sub n was the nth one, all keep going up. Then the integer 1 is mapped onto a1, okay? 2 is mapped onto a2, 3 is mapped, and so on, okay? So the numbers a1, a2, a3 up to a sub n and keep on climbing are the terms of the sequence. Now that's not to be confused with terms of a polynomial. It's the same word, different context, different meaning. The number a sub n is the nth term of that sequence. And the entire sequence is denoted by parenthesis, brace a sub n, close brace. Now, is this little thing on my screen that says you're screen sharing, is that blocking your reading that bottom line, or can you see the bottom line fine? See, on my screen, I can't see the a sub n, but I know it's there. Can you see that? Okay, good. All right. I thought that was something that was only on my screen, not on yours. Okay. So here's example 1. The terms of the sequence a sub n is equal to, okay, 3 plus a negative 1 raised to the nth power. Okay. Whoa. All right. Well, what are the domain of this? The counting numbers. So you're going to let n equal 1, n equal 2, n equal 3, n equal 4. So that's what you do. The first entry there would be 3 plus a negative 1 raised to the first power, 3 plus a negative 1 raised to the second power, 3 plus a negative 1 raised to the third power, 3 plus a negative 1 raised to the fourth power. You keep on climbing. Okay? Well, what is negative 1 to the first power? Negative 1. Okay? If it's an odd power, you keep the minus sign. If it's an even power, you make it plus. So this would be 3 minus 1. Okay? Well, 3 minus 1 is 2. This one would be 3. Negative 1 to the second power is plus 1. That would be 4. This would be negative 1 to the third power is negative 1. That would be 2 again. This would be 4. Next one, 2. Next one, 4. Next one, 2. Next one, 4. It keeps on climbing that, going that way. Okay? And at the very end, we'll put a dot, 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 meaning it's an infinite sequence. Okay? Now, that's it. That's all there is to it. Okay? Except that later we're going to say, does this sequence converge? And the answer is obviously not. It just keeps bouncing from 2 to 4 to 2 to 4 to 2 to 4 to 2 to 4. So there's no limit that you can say, well, somewhere out there it reaches some value. It doesn't. It keeps jumping from 2 to 4, 2 to 4, 2 to 4. Okay? So this is a sequence, but this sequence does not converge. Okay? Any questions about that? Okay? Let's just see how they did it. And there they have 2, 4, 2, 4, 2, 4, dot, 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 dot. Okay. Now here's number B. The terms of a sequence B sub n are n over 1 minus 2n. Now I wish they hadn't done all the work for you here, but this would be 1 because that's your n. The first value there, the first integer is 1. First counting number is 1. Over this one is there in the problem, 1 minus 2 times 1. Okay? And this is the next one would be 2 over 1 minus 2 times 2. The next one would be 3 over 1 minus 2 times 3. Next one would be 4 over 1 minus 2 times 4. And it keeps on going. Well, let's see what this gives us. 1 over 1 minus, well, 2 times 1 is 2, but it's a negative 2, so 1 minus 2 is minus 1. Okay, so this will be a minus 1. Okay, second one is 2 over 1 minus 4, so that would be a minus 2 thirds. The next one would be 3 over 2 times 1 minus 6, that would be minus 3 over 5. The next one would be 4 over a negative 7, so that's minus 4 sevenths. And it keeps on going. Now, the question here is this sequence. Does this sequence converge? Okay, does it end somewhere? Well, let's take a look. It starts at minus 1. It drops to negative 2 thirds. Actually, it's getting a little greater. And then it's going to negative 3 fifths, which is a little bit less than 2 thirds, well, greater than 2 thirds. And then now it's something, okay, negative 2 thirds, negative 3 fifths. Those are both greater or less than negative 1 half. This is now greater than negative 1 half. So it sure enough does look like this sequence could be converging. What is it converging to? Not too sure, but it could be. Because these numbers are getting less and less and less. Greater and greater and greater because they're negative numbers, but they never reach 0, obviously. But are they going towards 0? I would say yes, from the negative side only. But we're not doing that now. We're just naming the terms of a sequence. Let's go to, oh, and by the way, this is negative 1, negative 2 thirds, negative 3 fifths, negative 4 sevenths, and on. They're getting, the absolute value is getting smaller, but they're getting, which means they're less negative, which looks like they may be going to 0. Maybe. Okay? Here's C. The sequence C sub n is n squared over 2 to the nth minus 1. So n always starts at 1 unless you're given some other reason for it to be. So that'd be 1 squared over 2 to the first minus 1. Well, that's going to be 1 over 2 to the first is 2 minus 1 is 1. Okay, so that's 1. Okay, the next one is 2 squared over 2 to the second, okay, minus 1. Well, that would be 4 over 4 minus 1. That would be 4 thirds. Okay? Next one. 3 squared over 2 to the third minus 1. So this would be 9 over 8 minus 1 is 7. Okay? Next one. 4, fourth term, 4 squared, 16, over 2 to the fourth. 2 to the fourth, that would be 16 minus 1 is 15. Okay. Now I would like to go another couple. Okay, so let's do 25. That would be 5 squared over 2 to the 5th. Well, 2 to the 5th is 32. Minus 1 is 31. Next one would be 36. That's 6 squared over 2 to the 6th. That's going to be 64 minus 1 is 63. Okay? Next one would be 49. That's 7 squared over 2 to the 7th. That would be 128 minus 1 is 127. Okay? Now, even though back here it started at 1, it went something greater than 1, still greater than 1, still greater than 1, but a smaller number than this one was, and then from here on, your numerator outpaces your denominator. So now you get a fraction form less than 1, and every one of these get much less than 1, so sure enough, this looks like that probably is going to 0. They're not asking that now, but just to get you to look at it. That's why I wanted to do a few more than they did, because they stopped right here, which everything was still greater than 1. That one was 1. These were all greater than 1. I wanted you to see if you kept going, you're going to get things much, much less than 1. And sure enough, you did. Okay, so there is C. Okay, and there they have 1 4/3, 9 sevenths, 16 15ths, and ... We just did a few more of the ... Okay. Oh, here's D. Now D is a different kind of a sequence. The terms of a recursively defined sequence, D sub n, where D sub 1 is 25, and then every subsequent D is going to be, every n past that is going to be D sub n, the previous D, minus 5. So the first one is 25, the next one's 20, the next one's 15, the next one's 10. So this will be 20, 15, that one's 10, the next one 5, the next one 0, the next one negative 5, the next one negative 10, and guess what? That keeps on going and never converges. It goes more and more and more negative. That's a recursively defined. Now don't think that all recursively defined sequences will not converge. Don't even go there. It's just showing that's how you define a sequence recursively. You refer to the last entry and do something to it and give you the new entry, the next entry. Okay, so there's D. I think that's all of example 1. Yeah. And by the way, we're on, okay, now we're going to talk about what I was already talking about, limits of a sequence. Okay, now the primary focus of this chapter concerns sequences whose terms approach limiting values. Such sequences are said to converge. In other words, those sequences, they go on forever, but they're getting closer to some fixed number. Okay? Others don't converge, like that negative 12, negative 10, negative 15, negative 20, negative 20. No, the last one we did does not converge. It just keeps getting more and more negative. But if it does approach a limiting value, then we say it converges. And here's a sequence. 1 over 2 to the n. 1 over 2 to the first is 1/2. 1 over 2 to the second is 1/4. 1 over 2 to the third is 1/8. 1 over 2 to the fourth is 1/16. 1 over 2 to the fifth is 1/32. 1 over 2 to the sixth would be 1 over 64. 1 over 128. 1 over 256. 1 over 5 1 2 1 over 1 0 2 4 blah blah blah. Keeps on going forever. Okay, now take a look at that. Okay, every one of those is a fractional form. Numerator is 1. It never changes. Denominators are getting much bigger, much more rapidly. That's going to 0. Okay, that converges to 0 as indicated in the following definition. Definition of a limit of a sequence. If L is, let L be a real number, the limit of a sequence A sub n is L, that real number L. They're just telling you that. And here's how you write. The limit as n goes to infinity of A sub n is equal to L. That means that that limit of that sequence does exist, excuse me, and it's L. I am so sorry. I'm still anemic, and I am now losing strength fast. Hold on just a minute. Not nearly as anemic as I was a couple weeks ago, but in fact I had to go in and have a blood test again Monday, and the numbers came back. My wife was just reading them to me before she left. She got them on the portal, and they much improved. Still anemic, okay, still anemic. So I've got to go in next week and get blood work again just to see what's happening. Okay, so anyway, so if you're trying to get in touch with me first thing Monday morning, I'll probably be at the Kirkland Clinic. May or may not be able to answer a phone there because sometimes the signals are blocked. Usually I don't take my computer there, so I won't be able to do email because you have to get on their public email server, and that's usually a pain in the neck too. So I'll get home though sometime, not too much after 8. So if you need to get in touch with me, I won't be here right at 8, but I'll be here shortly thereafter. So the limit of a sequence is L, then you say the limit as n approaches infinity of A sub n is equal to L, meaning that nth term is getting closer and closer and closer to L, just like these fractions here are getting closer and closer and closer to 0. Now, that means the limit of a sequence A is L, written that way, if for every epsilon greater than 0, this sounds familiar, doesn't it? Back in our old derivative days, when we're just learning to do that, for every epsilon greater than 0, now rather than talking about a delta, we say there exists some capital letter M greater than 0 also, such that the absolute value of the difference between the nth term of the sequence and that limit that you think is there is going to be less than epsilon whenever that n, that nth term, n, is greater than that letter M. Now, let's go back a couple of slides. Remember this one that we said this got greater and then was still above 1, but then dropped to be lower than 1. If you had done capital M equal 1, this would never work. This would work here either for 2, because these are increasing here. Maybe not too much, but at some point they get, so they're getting closer and closer to 0. Now I can't say for sure that goes to 0, but my internet connection is unstable. So I'm going to quit talking calculus. Okay, did I break up some there? Anybody?
Yes, sir.
Okay. Okay, am I better now? Yeah, okay. I got a little message on my board said my internet connection was unstable, which is really bizarre because it's 5 bars the last time I saw it. I can't see it right now, but it was then. Okay, earlier. Okay, so you see you have to choose an M far enough out there so now these things do start getting closer to 0. If you chose this M, then the next one's greater and it's not converging, or it doesn't look like it is. This one's not as sure. It's getting less, but not much less, still greater than 1. That one's still greater than 1, but anything past that, and they get less than 1 and start going less than 1 big time. Okay? Slowly, but big time. Okay? So that's what we mean for any n greater than m. There is some m out there, so anything past that, you can guarantee that your difference between a sub n and L is less than epsilon. If that limit of a sequence exists, then the sequence converges to L. If the limit of the sequence does not exist, then the sequence diverges, period. Okay, diverges. All right. Graphically, that definition says that eventually for n greater than m and epsilon greater than 0, the terms of a sequence that converge to L will lie within a band that's between L plus epsilon and L minus epsilon. And these are the y values here. So they don't tell what sequence this is, but it's one that starts high, drops down, but then gets high again, but not as high as it was before, drops down a little lower than it did, goes up again, but not as high as it was before, drops down a little lower than it was before, and then goes up, still less than it was before, drops down again, and then once it gets into this band, it just stays there and just keeps oscillating back and forth above L, but getting closer and closer to L. Up here they weren't even anywhere close to L, but down here they are, and now they alternate above and below, above and below, above and below. Okay? Now, if you chose an M somewhere back here, no, it's no hope. You know, but if you choose an M past here, where is my cursor? I see it when, oh, there it is. Okay. Anywhere past there, you're always going to be between L minus epsilon and L plus epsilon. So there's your M value. There's some value out there that anywhere past that, you're going to be within. If you choose a smaller epsilon, so it gets closer, get that M on further out there, and because they're always getting closer and closer to that limit, at some point it'll be within that. Okay? So if a sequence a sub n agrees with the function f, okay, yeah, at every positive integer, and f of x approaches a limit L as x goes to infinity, then the sequence must converge to that same limit L. Okay. I wish you could read this here. It says for, now it's going to fade out. For n greater than m, that's what we see here, the terms of the sequence all lie within epsilon units of L. So the limit is L from there on out. Okay. Here is sort of a formal statement of that. Let L be a real number. Let f be a function of a real variable such that as x goes to infinity, the limit of f of x is equal to L. Now, this almost, if you're paying close attention, to me almost gets a little confusing, because before, when we were talking about sequences, we said that f is a function of integers only, positive integers only. Okay, but now they're saying let f be a function of a real variable, not positive integers. Okay, such that the limit as x goes to infinity of f of x is equal to L. if a sub n is a sequence such that f of n, now this x is any real variable. Now your same function here, but now you're only going to operate on positive integers. That's equal to a sub n for every positive integer n. Then if this part up here is true, this part is true. The limit as m approaches infinity of a sub n is equal to L. So this is any real valued function. This is only your function defined at the integral values, okay, positive integral values. So it says here, example 2, bottom of page 589. How are we doing on time? Okay. Find the limit of a sequence whose nth term is that. Okay. Now, frankly, I don't want to write this out. Okay, you could if you wanted to, but let's change this to a function, and the function would be f of x would be 1 plus 1 over x to the x power. Okay? Now, we want to find the limit of that function. If we find the limit of this function, that's going to be the limit of that sequence. Okay? Does this look at all familiar to anybody? This just happens to be e to the x. That's how e to the x is defined. Now, maybe I will write it out. Does anyone remember what let's see. Well, let's just start doing some of those. Okay, the first one would be 1 plus 1 over 1. Okay, so that's going to be 1 raised to the 1 power. That's going to be 2. The second one would be 1 plus 1 over 2 raised to the second power. Okay, that's 3 halves squared. That's 1.5 squared. 1.5 squared is 2.25. I'm pretty sure. You can check me on that. Okay, the third one would be 1 plus 1/3 cubed. That would be 4/3 cubed. Okay, I can't do that one in my head, so let me get my calculator. Okay, 4 divided by 3 equal 4/3. Okay, I gotta go to my mode and raise that, and just cube it. There's a cube key. And that's going to be 2.37 approximately. Approximately 2.37. Okay, let's do the next one. 1 plus 1/4 raised to the 4th power. That would be 1.25 raised to the 4th power. I get 2.44. Where is my pen now? There it is. It's approximately equal to 2.44. Okay, I said e to the x. I think this is just e. Well, next will be 1 plus 1/5 raised to the 5th power. So that would be 1.2 raised to the 5th power. That's 2.49. It's approximately. Come on, pen, where are you? There you are. Approximately equal to 2.49. They sure seem to be, that was 2, 2.25, 2.37, 2.44, 2.49. They're increasing, but at a much, much slower rate. Okay? Then you'd have 1 plus 1 over 6 raised to the 6th power. So that would be 7/6 okay, raised to the, whoops, that didn't take, my computer didn't do that right. 7 divided by 6 raised to the, no, okay, I know what's happening. I have to put parentheses. 7 divided by 6, close parentheses, and raise that to the 6th power. 2.52. That doesn't seem right, but yeah, that's right. 2.52. Okay, now we could go on like that for a while. Let's jump a few numbers, like 1 plus 1 over 10. So that'd be 1.1. That's easier to do, and raise that to the 10th power. Yeah, and you get 2. So I jumped 4 places, and I'm just going to write it. A sub 10 is approximately equal to 2.6. So it hasn't gone up much. Let's do a to the 100. Okay, that would be 1 plus 1 over 100. That would be 1.01 raised to the 100th. Now my computer may die on me somewhere here. That's 2.71. It's 2.7. So a sub 100, way out there, still only gone to 2.7 approximately. Let's do 1,000. My computer may not handle it, calculator may not handle it, but let's try. That would be 1.001. And that's going to be raised to the 1,000th power equal. Oh, it did do it. Okay, so a to the 1,000 is approximately equal to 2.717. So look, it didn't go up much at all. Let's see if we can go to 10,000. 1.0001 raised to the 1,0,0,0,0. Ah, look at that. A to the 10,000. Where is it? A, the 10,000th term of that. Aren't you glad I started skipping some? That's approximately equal to 2.718,146. Okay? Let's see if it'll do 100,000. 1.0000. I think that's where I end it, don't I? No, one more. No, end it there. Raised to the 100,000. Okay, if I can find my pen. Come on, pen, there you are. The 100,000th term in that sequence would be approximately equal to 2.71826.823 and it goes on. I'm running out of room. Okay, well, guess what? Let's do e to the 1 here. And I think this is just e. It's not e to the x, it's just e. Let's do what e is. I'm going to clear my screen. I'm going to e to the first power, and e is 2.718282846. So there are 1, 2, 3, 4. The first 4 digits here, we're right on the money. They get off on the 5th decimal place. The 6th digit is where it did. And if you kept doing bigger and bigger numbers there, you get closer and closer to E. So that's what that is. Now, all right. Sorry that took more time. Oh, we ran out of time completely. But if you look at that, that is E. Not e to the x, just e. Okay? And sure enough, that's what you get. Now, we're going to have to stop. Sorry about that. I wish we could have gone further. So on your last test, I may stick in one sequence or I may not. I'm guessing now I probably won't. Now, when will I have that out there for you? I can't do it now because I've got another class coming up. Then I got another one after that. But after those 2 classes are over, and if I don't do Brandon's paper right now, I'll do Brandon's paper first and then try to get that test out there to you. I think I already have it made out. I just got to check and make sure there's no improper integrals on it, and make sure if there are any on it, I'll probably give it to you and say this is optional. Well, in fact, let's look at it right now. Sorry about that. Let me see how to do this. Let's go to a screen share. Okay. Okay, what I think I'll do is get out of Blackboard. Out of PowerPoint. Well, I thought I could get out of PowerPoint. Why can I not get out of PowerPoint? Now I can. Okay. We'll discard that. Now let's go to... Oh, I already got it open. Here it is. Okay. Let's go back to here. And here. And 126 here. And what would this be? How many tests have I given y'all? 3. You have had the 3rd test. Okay. Let's see. There's 1. No, that's the syllabus. There's 1. There's the same 1. There's 2. There's the same 2. I must have used this for test 3. Let's see what test 4 looks like here. That's what we've been doing, isn't it? Oh, you can't. Okay, let me... Okay. Okay, I have to remind myself. We were doing integration techniques. This isn't it. Okay, that's not it. Okay. All right. Got to go back to this again. Okay. All right. Yuck! Every time I open it, that thing pops back up. Okay. Let's look at this one. No, that's the sequence. Okay. Not going to do that one. Okay. Let's look at this one. One of these days we'll get there. Okay. Now, let's go back to Zoom. Zoom meeting. Share screen. And this one. Okay, let me get this thing out of the way so I can see. This is such a pain in the neck. Okay. Yuck. Okay. I think this is it. Doesn't that look like the type of stuff we've been doing? Okay. Yeah. These are substitution, I think. Oh, this is just an integral. This is integration by parts. That's integration by parts. This is your sine and cosine functions. This is a trig substitute. No, this is the trig substitution. I think this is it. And this, I'm pretty sure, is, oh, what do we call that? Partial fractions. Okay. I think that's going to be your test. Okay. Now, I can't send it to you like this because this is in WordPerfect and none of you can read WordPerfect, I don't think. Can you? So what we'll do, I'll have to do a PDF of it. Do a scan on PDF and get it to you. So that will be your test. Okay. I'll try to do that. It's going to take a little while to get the PDF done, but sometime after 4 o'clock I'll try to have this out there for you. Now I'll probably put it in 2 places. One place is going to be, there's a tab after the weekly activities that says final exams, midterm and final. Now we didn't do a midterm, but I'll put the final out there. Okay, if I can't get it there, I'll put it in Blackboard message. I'll definitely put it in Blackboard message whether I can get it there or not. Okay, but that's what we'll do. So y'all okay with that? All right. So that will be pretty much what your test looks like. Any questions?
So this is the exam or the test?
This is your last test, which will be your final exam. Final meaning last test. It's not comprehensive. It just covers chapter 8. And there won't be any questions from chapter 9 on it. Okay? Does that answer your question?
Yes, sir.
Okay, good deal. And, I mean, you can always use tables on any of these that you can't do anything else with. So, but I think you can use all your techniques on these. But if not, use the table. Okay? Any questions? All right. Now, Brandon, you want me to look quickly to see if I can find your paper?
If you don't have enough time, you don't have to. But if you do, I mean, it doesn't matter.
Okay. I think I've got my email open, and I'll just type in.
I can see what day I sent it.
Yeah. And it's LEBLANC, right?
Yes, sir.
Okay, let's see if I can find you. I don't know why it wasn't showing up there. Why is there's something wrong here. I mean, my computer has been squirrely. I think I'm with Andy on this one. My computer has been squirrely all day. Let's stop this. Okay. Okay, it's searching. There it is. Okay. Subject is when?
On the 31st.
There. I think that's it right there. Goodness, this thing is so slow. I guess I've got too many things open. But I see it on the 31st, and it just says Brandon LeBlanc 1 ... X 19 kilobytes. It just hasn't opened yet. Okay, I don't know why. I opened it several minutes ago, and it's still just sitting here. So I think I'm going to have to shut some stuff down and go back and find it again, because this is just incredibly slow right now. So yeah, I think I've got it, and so I haven't printed it yet. So it was still in my inbox, and I will try to print it sometime after 4 this afternoon. Okay, good. Oh, there it is. Isaac Newton?
Yes, sir.
Okay, yeah. In fact, I'll see if I can print it right now. Let me make sure my computer, when my internet went out, it stayed on the same internet server. And let's see. Goodness gracious, this thing is slow. Oh yeah, I'll just print it right now. Okay, good deal, folks. So let me get out of this if I can find the exit key here. This is so bizarre. It maybe y'all are in the way. Yeah, there it is. There's the exit. Okay. And I still can't get out. I don't know what's going on here. So I think what I'll do is minimize this. I'll worry about that later. It's supposedly, I don't know, now it's having trouble printing, maybe it looks like. I don't know. Alright. I'll have to see if it printed. I have the door closed because the cleaning lady's here today. And let me get out of this, out of that. Okay. Any last thoughts, parting shots before we end? Okay, Andy, it may have been before you came in. Please do the student course evaluations. If you were in a first mini-term course, please do that as well. They didn't get this open in time for first mini-term, so try to do those as much as you can. Any last thoughts, questions? Now, I'll be here. I won't be in the class. I'm not going to do a Zoom or anything next week. Just send me your stuff. Send me your research paper if you haven't already. Send me your past test if you haven't already. And once I get the last test out there, the one you just saw, then get that to me as soon as you can next week. Okay? Are any of you graduating this term? I think I asked this question before. I don't believe you are. Are you?
No, sir.
No, sir. Okay. All right. Well, then I'll get your grades out there as soon as I can. Okay?
You said today was your last teaching day, like official teaching day?
No. I'll be teaching tomorrow, but this is my last one for Math 126. I'll be teaching tomorrow, and then next Tuesday, I've got one last class in my second mini-term class to teach. After that, woo, done. Yeah.
How's it feel?
It's feeling pretty good. Well, I'll have to get all these papers printed and graded before I'll feel anything. So after that, I think it'll feel pretty good. I love teaching, It's the administrative stuff and yeah, sometimes the grading and all that kind of stuff. But I love teaching. I really do enjoy it. Though this term with this anemia, it's really sapped me really badly. So I think it's time. I believe it's time for me to go. But it's been a good group to go out on. So thank you so much for being here. Y'all are one of the best attending classes I think I've got. Way to go. Thanks for that. And we'll see you when we see you. I'll still be here. Now, I won't have a Lawson State email address, but for a couple more months, December, January, maybe sometime in February. But if you need to get me before the 1st of February, because I don't know how long they'll keep this. And I can give you my Gmail account then. I don't know it for certain now. I don't want to give you a wrong number, a wrong name, but my wife has set it up. I've just got to start learning it. Okay. So it's something like FowlerCharles01 at gmail.com, but I'm not sure that's it. I'll have to check and see. But if you need me anytime before the 1st of February, email me on Lawson. I'll be checking emails, and then I'll give you my Gmail account if you need anything beyond that. Okay? Good deal. So I've stopped screen sharing. Take it easy, folks. Be safe. Please. The virus is running crazy right now. Hospitals are filling up, setting records every day. Please be careful. One of my instructors, her son came home from school, bringing it home. The whole family got it. The two sons were pretty mild cases. She and her husband didn't have bad cases, but they still have a terrible cough. The boys got through without any problem. You can't tell who's it going to hit badly, who's it going to hit well. Evidently, Nick Saban didn't have a bad case of it, but other people are on ventilators. So, I mean, it's hard to say. So take care, be safe, okay? All right, good luck in your future endeavors, and please do your student course evaluations. All right, bye-bye. If I could get it to end, there it goes. All right, take care, bye-bye.